When I submitted this abstract, I kind of had this concept in my head talking about the role of additives. And then I realized that's way too much information. It would be a 2-hour presentation, even if I just simplified it the best that I could. So among the audience, who has never made a paint, actually physically made a paint? No hands? Oh, okay. If you've never made a paint and dealt with the difficulties of making a can of paint, please go into your laboratory and make a can of paint. Try it. It's not as easy as it would seem. And so in order to cut my presentation short, you need these additives to make the rest of the paint work. If you're a resin manufacturer, you want the paint to work with your resin. Unfortunately, your customer who bought that resin needs to use something else to address issues that he runs into. And every paint manufacturer runs into these same issues, and they all use the same techniques because all the ingredients follow the laws of physics. So everybody's additives in some system works. However, the additive is only 1 to 2% of that total composition. What's the other 98%? That's what's important to keep in mind. The other 98% determines which additives will be needed to make the system work. So our company is proud of its impact on environment. Everybody is talking about sustainability. We've won several sustainability awards consecutively. We're in the top 5% of the industry. And our commitments to these sustainability goals. I'm not going to read these off to you. You can read them, should be big enough. The importance of each one of these is different for every customer, but they kind of all-encompassing. We're going to be talking about various technologies that are available to the industry based on these particular items. Where are they used? They're used everywhere. From the wall to the shell of the car. When I heard about a car without any paint on it, I immediately thought of corrosion. That film that's applied over that paint, that metal, is not going to provide corrosion protection. Or is it? I don't know. Maybe they're doing something they're not going to tell us about. But the principle is still the same. You could buy a white car and film it, whatever you want. Commercial vehicles are like that. They're all just wrapped. All right, we need wetting agents in order to get the continuous part of the coating onto the substrate. And I'm going to be discussing now these PFAS-free. That seems to be a big item of interest for paint manufacturers because the PFAS is now a scrutinized material because of its fluorine-carbon connection that is so resistant to degradation. And we used it for that property, but now it's come back to haunt us because these are now known as forever chemicals. And so much of the effort of the industry to achieve higher degrees of sustainability is to replace those PFAS materials with now called PFAS-free. And so hopefully you've read all these key points on this item while I spoke. We're going to be talking about a particular technology. If you look at these particular slides, you can see the change in contact angle, the wetting out of that droplet on the substrate. The flatter that drop is, the better, the wetter it is, the lower that contact angle. And then without and with on a plastic substrate, you can just see the effect. in our transition from solvent-borne toward less solvent because of the impact of solvent on the environment, some companies have switched their interest to waterborne technology. Waterborne is a very interesting technology. For the formulator, it's a big challenge, because when you make waterborne coatings, sometime during the transition of that coating from a waterborne coating to a solid film, it's no longer a waterborne coating, and everything we use to stabilize the particles that we put into this coating, the emulsion particles, the pigment particles, the fillers, and all those other things, they're no longer compatible and stable in the system because all the water's evaporated, it's gone. So what happens to the stabilization mechanism during that time? Fortunately for the formulator, he only has to prevent the flocculation of the system until the film is no longer mobile to reflocculate. Then it can just, once it can't move anymore, who cares? But that's the challenge. Take that waterborne coating as it becomes less and less waterborne to resist the physics, because physics says it's going to flocculate. And we say, no, we're going to keep it from flocculating, but only till the coating is no longer mobile enough to flocculate. So the sealing over variable substrates, the wetting out, the uniform wetting out of a waterborne coating system. PFAS was commonly used in the industry for its surface release properties, dirt repulsion, and also for block resistance. We have PFAS-free alternatives that provide very similar capabilities for paint film, to provide dirt release, to provide block resistance, and improve stain blocking. If any of you have specific topics you want to discuss further, in the tabletop room, look for the yellow tablecloth. We're there and we can answer more specific questions. This is the stain resistance of the first coat and the second coat of various stains. And then block resistance. Techniques are all described in the small print: heated, pushed together with pressure, and then taken apart. Hopefully, that we want to see is just full release, but the panel on the left you can see has stuck as we removed, and the layers have adhered to each other, and without on the right-hand side. These are very interesting materials. They have functionality, so they can cross-link in with the films to prevent the migration of these highly mobile species. Modified polysiloxanes are used commonly as an alternative and as surface-type agents. And they function across the whole board of these particular additives as wetting additives to lower the surface tension of water or your solvent system over a low energy substrate. At higher molecular weights, we actually use them because of their insolubility and incompatibility as defoamers. And in the old days, well, now we use them to replicate antique type appearances, which is typically called hammer tone finish. The appearance that you end up with is a metal that has been flattened with a ball peen hammer. That's why it's called hammer tone. That was a technique that was used to cover rough metal surfaces, to hide its surface roughness. modern manufacturing techniques make the metal much smoother. The RMS is much, much smaller. So now, today, they're only used to replicate antique appearances of modern manufacturing. So this modified PDMS material is used across the board for its either solubility, and as you modify it, for its incompatibility and solvency in various solvent systems. This material, for waterborne and for solvent-borne, not the same material, two different types, have hydroxyl functionality so that these particular molecules cannot migrate. If you're not aware of it, PDMS unmodified migrates. That's why it's used as a surface slip agent and so forth. However, when you cure the films, it continues to migrate to the most hydrophobic interface. So if you put 5 layers of film down, you got 5 times the amount of polysiloxane at the surface, because it's free to move. And you can remove it by washing it, and it's gone. These materials will not migrate because they cross-link into the system as a part of the binder. So each layer, there's the same level at the surface. And they provide then dirt release, stain repelling properties to the coating. And we're going to see the evidence of some of these. For solvent and also for solvent-borne. These are the solvent-borne examples. So these are surface-modifying additives that have a hydroxyl functionality added to them so that it can participate with melamine cross-linking, two-component curing, and so forth, to provide then permanent surface properties that don't relocate themselves. And so you can see, compared to the reference and the blank, without the visual appearance that you get from these surface properties, because they migrate to the hydrophobic interface and then cure there when the film is cured and no longer migrate or captured by the polymeric structure. Other PFAS-free examples, and these are now, this example is a non-reactive one, and you can see the impact on that, on those black panels. Different colors. Great impact on the visual appearance of these over various challenging substrates. Wood is a very interesting substrate for formulators because it's a natural substrate, has different degrees of porosity, different degrees of different types of waxes and oils at the surface. And so it's a balanced combination of wetting, spreading, and penetration, all simultaneously happening, that it's to control the contact between the coating and the substrate, and then the coating and the upper surface, the hydrophobic surface of that coating, to give you then these various appearances. And then there are other additives that are available to you to prevent the, well, in order to use pigments, you need a dispersing agent to help stabilize these particulates that we put within the film to prevent flocculation. The flocculated state is the lower energy state. That's why systems ultimately flocculate. So we use these dispersion stabilizing additives to enable the manufacturing and the production of these types of particulate dispersions in the system. And what we're going to look at is this is a particular dispersant system that is capable of self-structuring by itself. So in addition to dispersing these particles, it can associate with itself to provide then stability for prevention of separation due to gravitational forces and the density differences of the materials in the system. Pictorially, it's multifunctional, so it can capture actually more than one particular substrate. It has the capability of hanging on to multiple groups, what we describe as controlled flocculation. Not true flocculation because there's no contact between these particles. There's a polymer between them. That's the dispersion stabilizing additive that is capable of self-structuring to provide then interesting rheological properties to your coating, to prevent the settling of dense particulates that we put into the coating system, improve sag resistance without affecting its viscosity. We can actually show higher sag resistance in a lower viscosity than the reference. And then here's a surface additive that can support your effect pigment orientation in a coating. All right. Typically, we use shear to orient the flake, and then we used gravitational forces and compression forces. As the solvent evaporates, the volume reduces, and that film goes lower in film surface thickness to prevent these particulates from rotating. Now, think about when you have less solvent. Our solvents now evaporate much slower because we don't have 15% solids anymore, right? Those coatings don't exist anymore, the lacquers, the 12% to 15%. Now we use lower molecular weight materials that are, let's say, more fluid during the application process, don't evaporate, and now the film thickness is big enough that these flakes will actually rotate and move around and give us reverse flop. Now we think about how can we control this? How can we enhance this? All right, think about this. Now we use leveling additives from below of the applied film that are chemically designed to orient themselves to the most hydrophobic interface, which is the air interface. So here we're using leveling additives from below to keep those flakes from moving. So look at those two panels on the right. And these were done with effect pigments, metallic flake pigments, to provide the lightness. And you can see with and without this particular leveling additive, its impact on the orientation of some of these coatings now that are being developed that are challenging for metallic flake orientation. So just another approach of an additive that provides multi-benefits to your application process. Some very novel dispersing additives for your solvent-borne systems. They're cumene-free, tin-free, And they do all the things that dispersants are supposed to do. Disperse pigments, stabilize them, and be compatible with coating binders. Just comparison of fineness of grind, efficiency. Evidence of clarity in pigment 23, 7, and then co-grinding. Regardless of how you manufacture paint, these particular dispersants can be incorporated into the process to give you lower dispersion times, higher degree of dispersion that are compatible and stable during the paint application manufacturing process. And then the type of viscosities that you can expect at typical pigment loadings. The dispersants that I just previously described for solvent-borne systems also is available for waterborne systems. The properties that it provides is pigment dispersion, resistance to flocculation, and self-assembling properties so that the dispersant itself will participate in the long-term storage stability of your pigment dispersion to prevent materials from separating. The mechanism in aqueous systems is the use of other ions and materials and itself, its ability to associate with them in combination with and during the pigment stabilization stage, during long-term storage. It also has an impact on the orientation of flakes, as you can see here, of metallic flakes in a waterborne system. That's always been a challenge because water doesn't evaporate very quickly. It evaporates at its own desire, depending on relative humidity and so forth. And so the structuring of these dispersed particles is captured during the application process to prevent then the rotation of that pigment flake because of the structuring of the dispersing additive itself. Several examples with other effect pigments. In more realistic colors with other transparent coatings, pigment dispersions. And then the impact on, typically these would be primers, which high content of high density pigments. They tend to provide, these tend to separate and relocate themselves due to their gravitational preferences, and you can see from the example of the can, these are stability cans that have been just had the lid off and they're unstirred. The uniformity of the particular product and its addition and its ability to provide then corrosion resistance by keeping the pigment particles in their proper distribution. And our contributions to your sustainability, this is a new product. And it's a hard one to grasp in your mind because it's a universal dispersing agent for industrial coating applications. This has been common for the consumer architectural market, has always been available for quite some time. These are now suitable, these particular ones I'm going to talk about are for industrial applications. waterborne and solvent-borne, of a much higher performance level expectation than architectural coatings. Various binder systems and solvents that they're compatible in, it's like an eye chart. But there's only a few that have limited solubility and compatibility. Typically, I would claim they're pretty much all usable. Now, the requirement for dispersant, just step back in levels of presentation. Here are the requirements for dispersion. It has to disperse the pigment and keep it stable. That's given by its name. It has to be soluble and compatible in the system that you put it into. So that means in solvent-borne industrial coatings as well as waterborne industrial coatings, that dispersant has to be soluble and compatible until and provide that stabilization of resistance to flocculation until the coating is solidified enough not to be mobile. That's the requirement for dispersant. Always keep that in mind. That's always been the challenge. So here in a aldehyde-based resin pigment, you can see the type of viscosity we see off the spatula. Color, and these are all in various binder chemistries against the reference. Now they're in waterborne coatings. So here's another group of additives that we don't really think about. The dryers, the catalysts. It's a necessity, but now we offer tin-free alternatives. Dibutyl tin dilaurate was always the product of choice because that worked very well. But now we can replace it with tin-free alternatives that provide equivalent curing properties. Of course, the reformulation sometimes can be interesting because many customers don't like to reformulate. They just want to use the same amount that they've always used. So we have various grades. We modify the concentration so that you can use what you've always done in several formulations. And then for powder coatings, the PFAs have been used for introducing texture into powder coatings. So we have PFAS-free versions. As post-ads. And these particular additives are applicable to multiple chemistries, including chemistries that we haven't even tried yet and used, and the various curing technologies of these, because the function of these particular additives is prior to the solidification of the film. So if we do it before the solidification of the film, as long as it does not impact the curing mechanism, why can't you use it? So, just in conclusion of the various segments of the coatings industry, waterborne and solvent-borne technology exists and we offer multiple additives that alter and address the interfacial chemistry issues that you might run into by the combination of these different chemical materials. Our goal is always to increase the amount of biorenewable materials to displace the petrochemical carbons that we have in the system. And new challenge is to use some of our technologies for improving anti-fouling technologies, introduce self-healing, and increasing the multifunctional benefits that our additives can bring to a particular formulation. So in conclusion, come visit us at our tabletop. We're prominent. The yellow tablecloth is easy to find because it's the only one in the room. Thank you. Any questions?
I have one. What are the difficulties for replacing that tin-free? Oh, the difficulties in replacing the tin-free catalyst there.
Well, the tin catalyst has been so dominant in the industry because it provides surface cure, through cure, and many of the alternatives can only offer either equivalent cure at the bulk, at the surface, but not altogether. So our alternative is to use we have our own technology that we use to replace and enable then equivalent drying times, because that's the standard the industry uses, is through cure and surface cure. The challenge is to convince, because the customer wants to use the same percentage of material that he always has in his formula, that we make special versions so that it's equivalent to the standard acceptable solutions of dryers that you use as a replacement. What I learned from the dryer expert in our company is that particular segment of the industry tells you exactly what you get. The product is labeled as 12%, and it's the content that's item of interest, because the solvent that it brings to the system is such a small amount in your solvent-borne systems. Typically, this would be alkyd-type chemistries, that it's really insignificant. But we provide, on the label of the product, they tell you exactly what it is. Okay, it's either a 36%, a 40%, 10%, 6%, 12%. To me, that was interesting, because you have to make the dilution concentration in the amount that the customer is used to, because of the difficulty and the time involved with reformulating. I can give you a more efficient package. You can use half as much, but you have to reformulate everything.
John, I need to break in here. We're running out of time here, so I really want to thank you very much for presenting today. As far as the audience goes, you can always post your questions to him, and he can answer you in the Whova app. He can respond to you. So feel free to do that, or go see their exhibitor booth. But thank you very much, John, for your presentation.
Thank you.
Today.